Okay, so hi. So welcome. Today we have Justin Campbell speaking on Functor points and percent.
Okay. The organizers are organizing the seminar under the topic. They're inviting me. Yeah, so for those who don't know, I have a 2-week-old daughter at home, so any errors are due to severe sleep deprivation. So
We're very lucky to have Justin.
Great. So yeah, the first thing I want to talk about is kind of sort of a warm-up. So we really are interested in defining algebraic stacks at the end of the day, which is the kind of thing that BunG is. But it's actually kind of good to understand first how to view schemes as functors in the sense that stacks will be functors. So Nick talked a little bit about this last time. In particular, he mentioned this fact that schemes can be realized as a full subcategory inside of all functors on commutative rings. So I'll work in a kind of similar setting. So let me just call K a base commutative ring. I'm usually thinking about the case where K is a field, but it doesn't really matter. I'll just write C alg for the category of commutative K algebras. I realize this board is probably not very visible, so I'll try to just write on this and then immediately raise it, and then not use the bottom panel. So, and then continuing to introduce notation for stuff that Nick talked about. Yeah, and by the way, Nick did a great job of motivating a lot of the stuff that I need to talk about today. So hopefully I can be a little bit more brisk since he did such a good job motivating, and kind of get a little bit more into the nitty-gritty. So I'll write use the symbol for the category of all functors from commutative algebras to sets. And I write it this way because I really want to think about it as a category of free-sheaves. And you're going to say, well, wait a second, isn't a free-sheaf a contravariant functor? And yeah, of course, I mean, you can think about it as a contravariant functor kind of a silly way from this. Right, I mean, it's a free-sheaf on the opposite category of commutative algebras. Maybe it's also a free-sheaf in a more interesting way. So let me explain that. So in this approach, the very first thing you want to do is define affine schemes in some kind of slightly silly tautological way. So for me, affine scheme, everything over a base frame, of course, is just a representable functor. Representable functor from commutative algebra sets. So representable in like the standard usage of the word, right? There's some commutative algebra such that this functor is given by out of that commutative algebra. It's a covariant functor, so it's come out, I guess. And as we'll see, this word representable gets very overloaded in all of this business. So here I really just mean the kind of classic sense. So okay, so this kind of might seem like why on earth did you do things this way? So maybe hopefully I can convince you that this is reasonable. Well, a few things. So first of all, just of course, by definition, this category of affine schemes will denote it like this. It sits inside of category of free-sheaves as a full subcategory. Okay, and then by the étale lemma, right, it's sort of automatically the same thing as the opposite category of commutative algebras. Right, that's sort of like one upshot of the étale lemma is that representable functors are the functor from opposite category of commutative algebras into this category of free-sheaves is fully faithful, and the image is representable functors, right? Okay, so this is all kind of tautological insofar as the étale lemma is tautological. But psychologically, of course, we think about this category as some kind of consisting of geometric objects, right? And so we want to sort of think about it a bit differently than we think about the category of commutative algebras. And so we'll accordingly use a different symbol. So like if A is a commutative algebra, we'll think about the corresponding functor it represents. Again, as some kind of geometric object, and we'll denote it by spec A. But notice, there's no topological spaces or anything in this picture. And then also as another kind of automatic consequence of these definitions, we can also think about the category of pre-sheaves, this big ambient category where all of our geometric objects will live, as being really pre-sheaves on affine schemes. Okay, so I've really just said a whole lot of nothing so far, right? Very topological. So yeah, so I just affine schemes is opposite to the category of commutative algebra, so I can equally well think about these functors as contravariant functors on affine schemes, which we often do. We'll denote an affine scheme by a letter like S, like Nick did last week, right? And think about them as kind of the test objects with which we probe our pre-sheaves, our functors and points. Okay, to bring this down to earth a little bit, so Nick, like I said, did a good job of motivating this perspective. But just to kind of remind you of something he said, I forget how much detail he went into on this example, but let's say I have a commutative algebra that is presented in this manner. Some generators and relations, I'm assuming it's finally presented. That's not really important, but maybe it's might as well. So in that case, the functor spec A, it represents, if we unwind the definitions, right? This is given by the category of commutative algebras from A to B, which means it's really just a set of tuples B1 through Bn, which are solutions to the system of equations given by the Fs. Okay. So again, this is kind of what Nick was explaining last time. This is, hopefully it convinces you this is a very natural point of view insofar as algebraic geometry is about studying systems of polynomial equations. We view affine schemes as functors in this way, then you can see that the value of the functor is just the solutions of the corresponding system of equations. Okay, questions so far? Let me give an example of a non-affine scheme, so maybe a more interesting kind of example. So say B is a finite dimensional vector space. Okay, so I guess for the moment, K is a field. Probably doesn't matter at all, but just for the completeness. So then I can define the projective space on B, and I'll just define it as a functor. Okay. So let's think very hard about what does the projective space parameterize, right? What is like an S point of the projective space for an arbitrary affine scheme S? So it's going to look something like the following. So okay. So if I use the kind of function notation, I might think of its value in a particular affine scheme like this. Again, the way that the enable lemma works, right? This is maps of pre-sheaves from spec A into UP, or if you think about it as a functor on commutative rings, it's just the value of this functor on A. Okay, so what does this guy parameterize? So I want to say parameterize as pairs, L comma P, where L is a line bundle on spec A, and you might think that I'm kind of cheating here by using some kind of geometry because I'm talking about line bundles. But it's really, you can define these in terms of commutative algebra, right? It's like a locally free A module of rank 1, right?
Oh, sorry, that thing.
Yeah, thanks.
Causing up
No worries.
a buzz in the.
Yeah, that's what great. So on the one hand, the projective space. Okay, well, let me write out the definition, then I'll explain why it makes sense. So this is like a projective rank 1 A module, locally free rank 1 A module. And then we also have the datum of a map from L to the free A module with generated by P. And this is supposed to be kind of like a vector bundle injection. Which again is kind of sounds geometric, but you can formulate this condition in commutative algebra. So your vector bundle injection there's a few different ways to formulate it. I guess one way to formulate it would be like for any map from A to a field K, if I tensor up this map P K, it's injected. Okay, so it's some kind of universal injectivity. So I think another way to say it would be like P is injective and the co-kernel is flat or something like that, right? But basically what you want is, so if you think about this as a family, okay, this is the whole philosophy, right? So we're supposed to think about this as like some kind of family parameterized by spec A. Well, basically for every kind of geometric point of spec A, right, you should think that we have a line inside of the vector space V, right? And so you just want to make sure that when I like tensor up with some residue field of A or something, that I actually get an injection, right, the corresponding line into the extension of scalar D. Okay, so this is kind of the moduli space interpretation of projective space. Right, so I don't know about you, but to me this is much more evocative than however it's defined in Hartshorne. But yeah, I'm going to do it. So similarly, you can define the Grassmannian as a functor by kind of allowing L to be a vector bundle of rank R instead of a line bundle, right? Otherwise, it's the same definition. It'll be a family of R-dimensional subspaces. Okay. Questions about this sample? Okay, cool. All right, so these are supposed to be some kind of some interesting non-affine examples. And natural question at this point is, as Nick said, we're supposed to have this category of schemes sitting inside of all the pre-sheaves, and we might ask how we can identify them, right? Okay, so we like something like, well, like a full subcategory sitting in between affine schemes. And all pre-sheaves, we'd like to really just give some kind of condition to single them out, right? Okay, so in order to do this, one has to first make sense of what is a closed embedding, what is an open embedding, and so on. Since we're not working with there's no underlying topological spaces in this setting, you might struggle for a minute to think about how these notions should be defined. So let's do that. So the way that this kind of yoga works is we define properties of morphisms by essentially first doing the case where both objects are affine schemes, and then the case where the target is an affine scheme, and finally the case where both objects are arbitrary. So I'm going to give a whole sequence of definitions right now. So first of all, let's say X and Y are actually affine schemes. So then a map for X to Y is called a closed embedding. And for me, this is a definition, but you can state it as a theorem, try to compare it with like Artin and so on. Closed embedding, that just means that if let's say X is spec A, Y is spec B, then this corresponds to the condition that the map from B to A is surjective. That's all it means. Okay, and now we can jump to the case where X and Y are arbitrary. I get to skip that second step I mentioned because, well, you'll see. So X mapping to Y, where X and Y are arbitrary pre-sheaves, this is called a closed embedding. Following condition satisfied. So for any affine scheme S, and any morphism from S to Y, we require that, first of all, that the fiber product, okay, the base change, is an affine scheme. Certainly a closed embedding should be affine, right? If we have some intuition for how these things work. So it should be affine, and the map from S times Y, so from the base change to S is a closed embedding. Is this, we know what this means from the previous definition, right? So this is a good example of kind of a general yoga. Like I said, in general, you have to kind of do the case where first both are affine, then only the target is affine, and then both are arbitrary. But here, because closed embeddings are kind of required to be affine, the condition here is just that the base change is already an affine scheme, so I just have to do 2 steps. Okay. That's closed embeddings. What about open embeddings? Well, an open embedding should be something that's complementary to a closed embedding, right? Hopefully that makes sense. So let's say again I have 2 arbitrary pre-sheaves. And let's say I have a monomorphism from X into Y. Which in the category of pre-sheaves is just it's the obvious condition, it's just objective on points, right? So then I can define the complements of X and Y. This is again going to be a pre-sheaf. It'll be a subfunctor of Y, of course, and so this requires a little bit of thought, right? If you've never seen this before, you might make a mistake when you try to define this, because you might be tempted to say, well, maybe it's Y of S minus X of X. But if you think about that, that's not a functor, right? Because like an S point of the complement should be, remember, S isn't necessarily like a geometric point, it's more like a family of points, right? So at the point of the an S point of the complement should be a map from S into Y, which entirely avoids X, right? So that means that it should consist of those maps S into Y, in other words, S points of Y, such that the fiber product is empty. Okay, and here by empty, well, this is the pre-sheaf, but it's the, if you like, it's the spectrum of the 0 ring. Right, it's a very simple functor to write down. Okay, so this is the correct condition to define the complement. And now we can define open embeddings. So let's say X is an affine scheme. Sorry, I keep changing the names of variables. So let's say X is an affine scheme and U is an arbitrary pre-sheaf. Okay. So, and we say that U into X is an open embedding. So here, I'm not assuming that it's affine or anything. It's like U could be non-affine potentially. If and only if there exists a closed embedding of Y into X such that U is the complement of Y. So an open subscheme is something that's complementary to a closed subscheme. Notice you couldn't define things the other way, right? Like if I take the complement of an open subscheme, I get something that's not a closed subscheme, in fact, right? In fact, if you think about it, this is a great exercise. If you thought about this stuff, you're exactly going to get the formal completion of X along the complementary closed subschema. I mean, in fact, there's no single distinguished complementary closed subscheme, right? Because if I change the kind of non-reduced structure, it doesn't affect what U is. Like if I make Y, if I join some nilpotence to Y, it doesn't change U. And so the complement of U, in fact, is like the union of all of the potentially non-reduced scheme structures on Y. Okay, so we have to define things in this order. All right, and then next we do the case where X is arbitrary, and it's the same kind of trick, right? So monomorphism from U into X is called an open embedding. Same kind of yoga, right? So I can only have for any affine scheme S, then the morphism from S into X, the base change, this. Now the target is an affine scheme, so I know what it means for this to be an open embedding. That's what I've required. Okay, so always you have this philosophy that we're kind of probing our functors by affine schemes. If we wanted to find some property that we expect to be stable under base change, you can always just define it first in the case of the target as an affine scheme, and then in general by this kind of trick. Do this over and over again.
In this definition, is it true that U is always a scheme? Some scheme?
Yes, yeah, it will be. But I haven't defined schemes yet, right?
Yeah.
Yeah, it will turn out to be. This will exactly be a quasi-affine scheme, right? All right, so I'm almost to the point where I can define schemes. So finally, I need to define what is an open covering, right? So let's say I have a collection of maps from some UIs into X. All this is open covering. So this means that, first of all, each of the individual maps is an open embedding. Right there. Okay, but now I have to think about what it means for these to be kind of jointly surjective, right? Or for these to kind of cover X. And so again, I use this trick with the well, same kind of way that we define the complement. So the condition is for any affine scheme S, and any map from S into X, there exists an index. This is the condition is that this map is an open embedding for any I, right? And then if I have an affine scheme S mapping into X, there exists an I such that the base change is non-empty. Not the empty scheme. Right, so for any test scheme mapping into X, it meets one of the UIs, at least. So this is what it means to be an open covering. Questions about these definitions? Okay, so all of these things have, meanings and kind of the locally ring space setup and giving like alternate definitions. Of course, everything will turn out to be equivalent. But I mean, notice, this is much more general. Well, general in a different direction. Because all these things make sense. For example, like this makes sense for X being an arbitrary free sheaf. So the nice thing about this category of functors is that it contains lots of other objects of algebraic geometric interest in a way that the category of locally ring spaces does not, right? So locally ring spaces don't work so well. You can kind of do formal schemes, but you have to put a bunch of extra structure on the rings. You have to do some topology or something. And then for things like in schemes and stacks, it just really breaks down completely. So this framework, I would say, is more
Sorry,
flexible.
what breaks down completely?
Like the locally ring space framework, basically. Yeah, it's just not amenable to those more general objects, which maybe if you do classical algebraic geometry, you don't care so much, but in geometric representation theory, we encounter these more exotic objects all the time. So okay, so more on that later. All right, so to define schemes, so there's sort of two conditions. One is that probably the one that you immediately expect, right, which is that they're sort of covered by affine schemes in this sense. But the other condition is that they satisfy descent. Okay, hence the title of this talk. So, right here. Okay, so I talked about free sheaves so far. I'm going to define what is a sheaf. What is a Zariski sheaf? So X is called a Zariski sheaf. If so, for any affine scheme S and any open covering, just make sure I use the same notation. Yeah. So for any Zariski open covering, for here, I'll also require the UIs to be affine. It doesn't really matter so much, but I can do this. Okay, the condition, well, the idea is, right, if I have a bunch of maps from the UIs into Fs, which agree on the intersections, or the fiber products, however you want to think of them, then I should be able to glue to a map out of S in a unique manner, right? And so there's a really kind of slick way to say this, which is follows. I write the condition, and then I'll say let's map to a certain equalizer and isomorphism. So okay, so this sheaf condition, imagine most of you have probably seen this before, maybe not in this exact context, but maybe for topological spaces or something. You can formulate the sheaf condition as the map from the S points of X map to the equalizer of this diagram. So if I have a section on UI, I can map it to a section on this overlap in two different ways, right? And so I can form this kind of equalizer diagram here. X of S maps to that, right? Because if I have a section that kind of glues to a section over all of S, then it'll certainly agree on the overlaps. And the claim is that this map is an isomorphism. Or bijection. Exactly, I guess. Okay. Questions about that definition? Same kind of thing you do for sheaves with topological spaces. It's quite analogous. Yeah.
How is that diagram viewed as a set?
Well, it's not. It's a diagram of sets, and then the equalizer is a set, right? So it's the subset of this product, such on which these two arrows are equal.
Oh, okay.
Yeah. It's an example. It's really the limit of this diagram, right? Equalizer is just a word for a limit of a diagram of this shape. All right, so now I can define schemes in this Functor points setup.
Can I just ask a question?
Yeah, sure.
Why is there equal to y?
the affine scheme, how do you guarantee it doesn't change the? Well, sorry, I just don't see how they were do the same.
Yeah, you don't have to require it, so like, the only difference is like. Instead of talking about the UI points of X, I would have to talk about maps from UI into X, right? If the UIs weren't necessarily affine, because it's like the unit lemma doesn't apply if the UI aren't representable, but you could still make sense of this condition and it would be equivalent. And the reason is because like any open covering by possibly non-affine things can be refined to a covering by affine things.
Okay, so in this covering that, like, think of it.
These UIs don't have, nothing here has to be affine except for S.
But can I refine that definition, like think of it in terms of size, can I refine it to UIs to be in the affine scheme and that still be okay?
Only if X were a scheme, generally, probably couldn't, right? Yeah. If X is say like an affine scheme, then any open covering can be refined to a covering by affine schemes. That's kind of like one of the axiomatic things that goes into group topologies, but I'm not trying to do that sort of general nonsense really. But yeah, all of this can be put into some really general framework. Okay, so that definition gives us singled out a subcategory inside of all pre-sheaves, which is the category of Zariski sheaves. Okay, now this is still includes a whole bunch of stuff that you might not consider to be geometrically reasonable. You know, certainly schemes are much more specific than this. So the other condition is the one that, you know, looks kind of similar to the locally ring space definition, which is that we should require it to be covered by affine schemes. So it's Zariski sheaf. It's called scheme. There exists an open covering. Where the UIs are affine. So if you like, I kind of baked it in here. There's really two assumptions, right? One is that it's a sheaf, it satisfies Zariski descent. The other is that it's covered by open affines. And you know, why do I require this sheaf condition? Well, one really kind of silly example you could think about is if I took if I took a bunch of affine schemes, right, and I just took their disjoint union as pre-sheaves, okay, which means just naively take the disjoint union on the level of points. That is a weird thing geometrically, because if you think about what it looks like, if I have a test scheme S mapping to that disjoint union, it has to land in exactly one of the components of this disjoint union, right? Whereas geometrically, if like the test scheme S were disconnected, you would want to allow it to land in possibly multiple components, right? It could be separated like that. So, so what you have to do is take that disjoint union and then sheafify it. Okay, so the disjoint union is in schemes or in sheaves, it's not the same thing as the disjoint union of pre-sheaves. And so anyway, if you take that weird disjoint union of pre-sheaves, that's something that's covered by affine schemes, right? But we don't want to view that as a scheme. It's really a non kind of geometric object. Maybe this should have come like before the definition of scheme, but it wasn't really necessary. Just a little statement here that's quite important, which is that the inclusion of sheaves into all functors, this admits a left adjoint, and that left adjoint is moreover usually denoted by a symbol like L or something. This is what's called sheafification, right? So I can take any pre-sheaf and I can sheafify it in a universal way. It has the universal property, which is specified by this jointness, right? You might very reasonably ask what does exact mean, because we're talking about sheaves here, not dealing groups or anything. But this really has a meaning kind of in any category. This just means it preserves all finite. Okay, so being a left adjoint, it preserves all colimits. Certainly it preserves all finite colimits, but what's not immediately obvious is that it also preserves finite limits. Okay. So it also preserves things like equalizers, which is really important when you're doing these calculations with sheavifications. And it's kind of you know, you do have to really get into kind of the nitty-gritty of like this Zariski topology. Like basically the idea is you can realize this sheavification as some kind of a filtered colimit. The idea being like, you know, if I take all those affine opens inside of a given affine scheme, the intersection of any two is again an affine scheme, right? So that thing is kind of co-filtered. So I can realize this the sheavification is some kind of a filtered colimit, and filtered colimits can be defined. So that's kind of what's going on technically. All right, so that's it for schemes. Some of you will probably find this interesting, and some of you are like, well, no. Sorry. All right. Any questions?
I do have a question,
Yeah.
but I think you're gonna answer it later.
Sure.
Which is, you mentioned that the low play ring and formal scheme formalisms don't really hold up in kind of the BunG setting.
Yeah.
Is it for the same reason that Nick was talking about, where considering things up to isomorphism is kind of the wrong thing to do, or is there a more subtle?
No, that's exactly right. And I shouldn't say that like stacks fit into exactly this framework, because I do have to kind of upgrade slightly, which is I have to consider functors valued in groupoids, which is the next step.
I see.
But it's all quite analogous to what happened here.
So kind of so far, you haven't really introduced anything that helps with this kind of isomorphism subtlety, but since we're working with sheaves and you can easily have it valued in groupoids instead of sets, that's kind of what
Exactly.
Exactly. Thank you.
Yep.
I guess I have a slight question.
Uh-huh.
In the Campbell scheme, we actually need the open sets to be isomorphic sort of on their image. Should we not be insisting as well that UI is an isomorphism of functors to X cross over UI, the fiber product, or is that
Sorry,
not
say
needed?
it again. So
So it would look to me like this is just saying it sort of there exists the oh, I see. No, you're insisting that those are open. That's enough, isn't it?
each individual one is an
Each
open
individual
embedding, and
one
they're
is an
jointly
open.
surjective.
Perfect. All right. Sorry. Yes.
Yep.
I see that will work.
Mhm.
You don't need to. I was thinking you might need to like do a UI cross X isomorphism or something.
Well,
like
yeah,
that.
they're
I don't think you need it.
you're talking about like the triple overlaps or something, or
No, just the fact that it's sort of this literally, you know, the open set is isomorphic to the functor UI.
yeah, they're monomorphisms, right? So
Yeah.
yeah, that's right. So the intersections are the same thing as the fiber products.
Absolutely.
Yeah. Okay. So, you know, there's a couple of other things. Maybe I'll just skip over it for the sake of time, but there's a few other things you would want to check, you know, setting up this framework. Like one thing is, it's actually not immediately obvious from this perspective that an affine scheme is a scheme. Right. So like it's clearly covered by affine schemes, it's covered by itself. But the descent condition, right, the fact that an affine scheme satisfies Zariski descent is really a theorem, not, you know, it's not immediately obvious. It basically is the same proof as the proof you give in the locally ring space setup when you check that the structure sheaf is a sheaf. Okay. So if you check this, essentially what happens is if you're trying to prove an arbitrary affine scheme is a sheaf, well, you know, any affine scheme is like basically can be realized as a limit of copies of the affine line, right? Because it's like it embeds into some huge product of copies of the affine line, and like it's defined by a bunch of equations. So it's really like an equalizer of two maps between possibly infinite dimensional affine spaces. So you can actually just, since sheaves are stable under all limits, which is more or less equivalent to this statement, you can reduce the decay to the affine line, and then it really literally is like the same proof as the one you find in Hartshorne that the structure sheaf is a sheaf. Like the exact same commutative algebra. Okay, so that's one thing. Yeah.
That's that partition of unity argument, right?
Yeah, exactly. I mean, there really is, obviously there has to be some non-trivial commutative algebra input somewhere. I haven't done anything like that, right? And that's actually where it comes in. It really comes in to prove that an affine scheme satisfies descent. It's like that I think I erased it, but the affine schemes sit inside this.
Wait, sorry, you're saying the phrase satisfies descent, what does that mean?
Is a Zariski sheaf. Yeah, satisfies Zariski descent. Same thing as is a Zariski sheaf. Yeah, exactly. Like if I take X to be an affine scheme, I have to check that this condition is satisfied. And again, that will reduce to some commutative algebra lemma, because at that point, you're talking about everything inside this affine scheme. You can formulate it in terms of commutative algebra, and yeah, it's a standard kind of.
Isn't this just the like back? Isn't this just the condition that a pre-sheaf is a sheaf? Maybe I'm missing something.
Yeah, absolutely.
Oh,
That's what this means.
So
The definition of a sheaf. But I'm saying for X being an affine scheme, it's not totally obvious that it satisfies this condition. There's a little bit of commutative algebra to do. Like Aaron said, it's kind of like a partition of unity argument or something. No matter how you set up algebraic geometry, you'll have to do this proof at some point, right? You can't avoid that particular bit of work. All right, so I think we're at halftime.
Oh my goodness, yes, we are. All right.
All right, so
I'll make sure. Pause this.
okay. So one reason why I like spent all this time talking about schemes, even though the points against stacks, again, part of it was just by way of analogy, because maybe if you've seen this, then the definition of a stack seems more, or I should say an algebraic stack seems more motivated or something. But also, like, as far as I know, this material is not in any textbook. If somebody knows one, that would be awesome. Like, please tell me, but it just seems to be totally absent. So anyway, I find that strange. So
What material, this one?
yeah, like the definition of a scheme, like this definition of a scheme.
You can't that's project this time.
Sorry, is this definition of a scheme in Stack's project?
No, the geometry of scheme book. It's there.
Oh, maybe.
By
It's there.
Eisenberg
I
Harris.
found the chapter there.
There's some discussion of Functor points there, but I don't remember. Yeah, maybe. And my memory from that book is they take kind of a hybrid approach. Like I don't think they kind of set things up using Functor points from the beginning, but yeah, there's definitely some discussion of that in that book. Anyway. Yeah, okay, so if you count Gates, Rosenblum, yes. Yeah, I mean, of course, that's much more general because they do kind of schemes, but yeah, in particular, that's totally fair. Sorry?
The only textbook on right geometry I know.
Great, yeah. You'll love this lecture. So yeah, I would say, yeah, in the classical setting, like there's no, I don't, maybe it doesn't serve, maybe there's some reason for that, but anyway. I definitely found it difficult as a grad student, so I pick up some stuff, so that's why I'm talking about it. All right, so next, we're going to talk about stacks. So stacks are, as I said in the abstract, they're this kind of natural sort of categorification of sheaves, where instead of taking sheaves valued in sets, we take sheaves valued in groupoids. So which again, I think Nick did a great job of motivating. We want to allow for the kind of automorphisms and isomorphisms between these various geometric objects that appear in families, right? In this moduli space. Like moduli curves, G bundles, and so on. We have created functors valued in groupoids. And here I mean like one groupoid. So these are like there's 1, 0 categories. So I don't know if everyone has seen this kind of notation. Like the first index is like in up to what level the morphisms go. So we have 0 morphisms and 1 morphisms. And then the second index is like imposes an invertibility condition. So the 0 here means that 1 morphisms are required to be invertible. If I did 1, 1 categories, that would be like ordinary categories. Okay, so the first thing is to define, well, we had pre-sheaves and then we defined sheaves, so we have to define pre-stacks. So these are just functors. So these will assemble into a 2, 1 category. If you're kind of scared of 2 categories, that's totally reasonable. So just I invite you to ignore it. Really something you can kind of sort out later. So 2 category of pre-stacks is just arbitrary functors from commutative algebras to groupoids. This is an annotation for groupoids. And if you like, this is contravariant functors or pre-sheaves on affine schemes valued in groupoids. Same thing by the unit, right? Okay. So it's totally analogous to this category of pre-sheaves, except now our points are allowed to have automorphisms or more generally isomorphisms between them. Yeah. So you should say like this is the kind of thing that I'm just going to gloss over probably in the future. So since the category of groupoids itself is really a 2,1 category, functors into it have to be defined appropriately. I'm not going to do this in detail, but the kind of thing that comes up is like, let's say I have a pre-stack and I have maps F from S1 to S2 and G from S2 to S3. Part of the data of this pre-stack the following kind of thing. So I can write down a triangle like this. Right, and zeros are composable. So this is like X of G, and this is X of F, and this is X of G composed F. And you really require an isomorphism, right? These are groupoids, right? And these are maps of groupoids. And so I really require an isomorphism between these two maps of groupoids, right? So, and moreover, these isomorphisms satisfying natural coherence conditions and so on. And this is the kind of thing where, because we're talking about two categories, you can do it by hand. It's kind of a pain, at least for someone like me that's really bad at combinatorics, but it's doable. As soon as you get into kind of things like more complicated than one groupoids, if you do kind of higher and higher categories, it becomes quickly unmanageable. And there's this whole technology that's developed for that. But this can be done by hand if you're really determined. Okay.
Sorry, here the CL and groupoid are viewed as one category.
No, CLs is the one category, but groupoid really needs to be viewed as a two category. Okay. Yeah, I mean it's a 2,1 category, so there's no non-invertible two morphisms, but yeah, you do need to use the two isomorphisms, right, to formulate this kind of thing, right? Yes, it is important. Although again, if it's like going to prevent you from following, please ignore it. So now I can define stacks. And so before I just defined Zariski sheaves, but as we'll see shortly, and I think we kind of alluded this to this last time, for stacks, it's really important at some point to use stronger topologies than the Zariski topology. So I'll define sheaves in kind of various topologies, and the definition is really the same in all cases. So you could do things like Zariski topology, or you could do as we get kind of progressively stronger, the étale topology, smooth topology, the fppf topology. You have notions of étale covering, smooth covering, fppf covering, FPQC, but I won't need it. Okay, the condition is for any covering, it's risky or whatever kind of covering, where here the UIs and S are all affine schemes. We have the following condition, and I'm going to formulate it in a way that's totally analogous. Do I have enough room? Okay. Totally analogous with the sheaf condition. So let me write it and then I'll try to explain what it means. So here it really is important to write fiber products as opposed to intersections, right? Because as soon as you're talking about things that are not Zariski coverings, things like étale coverings or smooth coverings, they tend to not be inject, they tend to not be monomorphisms, right? So fiber product is important. Okay, but there's a third term here. And this appears exactly because of the added categorical complexity of the groupoids, right? And here this limit, this has to really be interpreted as sort of a 2 limit. Sounds a bit scary, but it does have really a well-defined meaning taken in groups. So I'll try to elaborate a little bit on what that means in a moment, but for now, let me just point out, this is totally analogous to what happened for sheaves. It's just that we need a further term, right? So secretly, that equalizer that appeared in the definition of a sheaf was the truncation of a certain cosimplicial object, right? So there's a whole bunch of higher terms going off to infinity, and we only considered sort of the 0th and 1st term, and that was sufficient because we were working with sets, okay? But as soon as you're working in a 2 category like groupoids, the totalization, which is to say the limit of that cosimplicial gadget, it's not the same thing as just taking the equalizer. You have to truncate 1 degree higher, and then you're fine. Okay, you can just take the limit of this thing. Okay, as long as the limit is interpreted appropriately. Okay, so I think probably a good idea for me to spell out, like what the groupoid on the right side actually is explicitly. But let me just say there is some kind of general framework of like limits in a 2 category into which this fits. And again, this falls under the domain of things I wish someone had told me when I was a first year grad student. It's like, you can go and read what is the FGA explained article about this. It makes it seem makes it seem way more complicated. Okay. Maybe just I don't know. Maybe this is cheating somehow for some set theoretical reasons, but I think it's totally fine in practice. It's kind of like Nick said, there's this whole fibered category formalism, but psychologically, you really want to think about these things horizontally rather than vertically. So let me spell out a little bit more. What is this limit, right? Of this kind of truncated cosimplicial thing. So an object of the right-hand side. So it consists of sections SI in X of UI. So these are objects of these groupoids, right? For any I. Together with isomorphisms, alpha ij, SI restricted to the double overlaps, right? 2 different ways. And notice what was a condition, right? In the sheaf definition, we just required that these sections were equal. Now it becomes a structure. It's an additional isomorphism, additional data, right? And now there's a third thing I have to say, which is now there's a condition on these isomorphisms, right? Satisfying. I'll kind of leave it as an exercise, right? It's a natural cocycle condition on the triple overlap. Okay, so there's some kind of natural condition that if you write it down, there's probably only one thing that you can write down. And then let me say, I'm supposed to tell you, this limit is supposed to be not just a set, but actually a groupoid. So I also have to tell you, what are the isomorphisms in that groupoid. So an isomorphism, the notation I use, so from say the SI alpha ij's to the TI data ij's. Tell you what this is. So this consists first of all, of isomorphisms. I call them phi from Si to Ti, and this makes sense because these are objects in the same groupoid, right? So I have these isomorphisms. And now there's a condition on these isomorphisms. I need to give myself room. I'll go to panel. Such that a certain square commutes. So this is like the restriction of the alpha ij. I just don't like the restriction. Or sorry, this is the alpha ij's. This is the restriction of phi. Phi. Here's the overlap. Theta ij. Ej. The overlap. And here I have the bj. So this is required to commute. Okay. So that is the groupoid, and this is required to commute, of course, for any. So this is the groupoid, which again, if you kind of think about what is a limit in the two category, and you write down below this diagram, you exactly get this groupoid. Okay, so you don't have to like memorize everything in that Vistoli article. You can just remember this. I think it's a little bit easier. All right, so at the end of the day, I've defined a bunch of categories of stacks. So kind of an increasing order like this. And now something I'll point out at this stage is that smooth stacks in the smooth topology and stacks in the étale topology is not something about stacks. Same thing is true for sheaves. These are equivalent. The same condition, in fact. Just kind of like a standard fact about these topologies. So you'll just leave it at that. You just say satisfying, even though satisfying smooth descent is a priori stronger, in fact, it's equivalent to satisfying. You don't really need to talk about the smooth topology much.
When is the literature consistent on using the word least étale topology?
Sure.
I keep seeing it used when they're discussing stacks like the least étale topology. Is that different from just the?
Is it different? I don't actually know. So it's some other notion. Okay.
Yeah, I feel like I've seen definitions like
Yeah.
smooth
Sorry.
maps with étale maps between the smooth maps and stuff like that, but
I see.
yeah.
Yeah, I'm not sure I can comment on it, but okay. Yeah. Yeah. The way that I've defined it, the étale and smooth topology is the same. Okay, so what I've not done is like motivated why I need to consider something besides the Zariski topology in the first place. Oh yeah, before I do that, one other thing. There's this fact that we have sheavifications, right? And this will actually, I'll need this for my example. So let me say like star is like Zariski or Tal or fppf. The inclusion of stacks in any of these topologies into free stacks admits an exact left joint. This we call like L star or something like that. Okay, and here the words exact and adjoint should be understood in the correct two categorical sense. It's nothing too crazy. It's just like the the comms in these categories form groupoids, right? So like for example, to define an adjunction, like you should require that there's an isomorphism of groupoids between the appropriate com sets, and then exact means commutes with finite limits is the substantive part in the sense of this kind of sense of limit, right? completely analogous to what happens for sheaves. Don't need to think any more about it. Now I'm going to give some examples. Any questions of these definitions? Yeah.
So to define these topologies, are you viewing like affine schemes as three stacks by saying the set of the groupoid?
Yeah, exactly. Yeah, so that's something that I neglected to mention, which is that three sheaves. Really should have called them this notation, right? Consistency. We don't switch in the middle of it. So yeah, there's a fully faithful functor. There's an inclusion like this, which is just any set can be viewed as a group. Right? So a particular functor value set can be viewed as a functor value. In groupoids, this is strictly an enlargement.
So are the affine objects which you're using to define these the pre-sheaves or like the maps from community development?
They're really things that are represented by community developments, particularly. Because remember, the domain category for this category is the same as before. I just changed the target, right? So everything in this category is still kind of like a co-limit of affine schemes, but it's just a co-limit in some two categories, right? So it's still probed by affine schemes. All right, so now I want to give.
For us, we're going to look at PF steps.
You can kind of set things up using fppf or étale topology. What I want to convince you right now is that you can't get away with the Zariski topology. Okay. So I don't think I've really given any examples in this talk, but again, I'm going to blame that on Nick because he said he did such a good job last time. So let me give some examples to show you why these topologies might be relevant. So let's say G is a group scheme over K. You know, I'm probably secretly thinking about K as a field and G as an algebraic group or something. Maybe, let's see, do I want to make any assumptions? Yeah, okay, let's say it's a group scheme over K. Okay, so then I can define this thing. I think Nick called it like BG naive or something. I guess I'll call it BG triv. So this is the thing that classifies trivial G bundles. So it's kind of a silly functor. It's just like the groupoid with one object. I'm gonna call it point or something, and the automorphisms of point are defined to be G of S.
BG.
Triv.
Oh.
Triv. It's the stack that classifies trivial G bundles. So it's a bit silly. Okay, so this is like sort of the thing you start with, so it's a pre-stack. Okay, and from this I can sheafify, right? So let me call, oops, I shouldn't use this. Nick talked about this a bit last time. So let me call BG star the stackification in any of these topologies of BG triv. Okay, so if you untangle the definitions, you see that this exactly classifies principal G bundles, which are locally trivial in the star topology. Okay, that's exactly what this stackification procedure does, right? You're gluing together local sections with respect to these topologies. So locally it'll be trivial, but globally it may be non-trivial. So I want to make a few remarks about this. So one is that if G is smooth, then the étale sheafification is equivalent to the fppf sheafification. And the reason is because like any G bundle which is locally trivial in the fppf topology, it'll in fact have a kind of a smooth local trivialization, which is like sort of the universal thing. It's like the total space of the bundle itself, right? Take the fiber product with itself over the base. That thing is going to be trivial. And so it'll be locally trivial in the smooth topology and therefore in the étale topology because of this thing I mentioned. They're the same topologies. So this is one thing. So anytime you're talking about smooth group schemes, if you think of this fppf thing as like maybe the strongest condition you would reasonably impose, I guess you could also impose like FPQC descent or something, but if G is finite type, that'll be the same thing as fppf. So anyway, so this is probably the thing you most often see defined as like the classifying stack, right? Locally in the étale topology. And again, it's reasonable as long as G is smooth. You know, in some cases, like for example, for GLN, Zariski locally trivial GLN bundles are sorry, étale locally trivial GLN bundles are actually Zariski locally trivial. They're vector bundles. So I don't know, maybe it's some over here 90 or something, but yeah, this is true. However, this tends to not be true for other groups. Okay, which is a big part of the reason why we can't get away with using the Zariski topology. So our many group schemes G, BG Zariski is not the same thing as BG étale, which is to say there are étale locally trivial G torsors which are not Zariski locally trivial. Let me give an example. Let me give an extremely simple example that might not be the most relevant, but pretty simple. So you could do something just like G equals the multiplicative group. Sorry, not that's not okay. G is the, of course that falls under this example. G is the group of second groups of unity. Okay. And so then we can consider the mu2 torsor, which is like the squaring map. I guess it's not important that it's 2, right? Any un. So then I have the map that's like z goes to the n. So this is a un principal bundle for un. It's locally trivial in the étale topology. Well, I guess fppf if p divides the characteristic of n, but it'll be locally trivial in the étale topology and is prime to the characteristic of the field or the base ring or whatever. So anyway, so as long as so this is, what I mean to say is this is not Zariski locally trivial. If I'm in characteristic 0 or whatever, it'll be étale locally trivial, but not Zariski locally trivial. Okay, so this is like one way in which this kind of thing can happen.
BG Zariski like anyone?
Oh no, I don't think so. I don't think it's some kind of really crazy map geometrically. Yeah, I think what I would say is that BG Zariski is something kind of unnatural.
There is, I actually asked Nick about this, discussing the setup in the seminar. It's true if you have a G torsor for a reductive group G over a curve, that it is actually Zariski trivial. In fact, there's a stronger theorem which will prove eventually the Drinfeld-Simpson theorem that it's trivial even if you remove a point. But that won't help you for BunG because it needs to be sort of like Zariski.
You need families.
For over S times X. So it, the classic failure is the example offers things like surfaces or things like that. So
right. So even though G bundles for a reductive group are Zariski locally trivial over a smooth curve or something like that, ultimately we need to consider families of such, and those will not be Zariski locally trivial on the base.
Sorry, I have a notation question.
Sure.
So does this just mean, like, when you say G bundles locally trivial with respect to star, you just mean like one of the topologies, like étale, et cetera, et
Yeah.
cetera? So what's the L?
Oh, it's sheafification in that topology, or stackification in that topology.
Oh, okay.
So I just universally make it into a stack in that topology, and it has a concrete meaning, which is just it classifies, like it says there, G bundles locally trivial in that topology. But if you unwind the definitions, That's the same thing as taking this trivial thing and stackifying it in
Okay,
that topology.
that makes sense.
Yeah, and there are much more interesting examples of this, by the way. So like, you could also do something like, if like B is a kind of non-trivial quadratic space, over some field or something like that, you can actually define a ON bundle. Okay, and the idea is like any quadratic space is going to become trivial over some extension. You know, let's say you're over R, right? Like you can have non-trivial quadratic spaces, but over C they all become isomorphic, they become trivial. But of course, that's an étale based change, right? Base changing from R to C. So, which is locally trivial. So étale locally trivial, not Zariski.
I don't know if I mentioned this, but that was actually the example Brinfeld told us we need to mention.
I think it was in the original abstract.
Yeah.
Which is probably how I shot it.
Okay, great.
So yeah, great. And so this gives you another class of examples. So in case it's not clear, the way you go from this quadratic space to this torsor, it's kind of the same way that you go from like a vector bundle to a GLN torsor. Right? You take trivialization to the first one, okay, which will exist locally, but not globally.
Okay, what's a quadratic space?
Like just a vector space with the quadratic form.
Oh,
Yeah. So these, you know, you have non-trivial things like the Minkowski form or whatever. Yeah, and so this is neither here nor there, but I think I didn't know this before I prepared these lecture notes. It's really cool. So there's a theorem due to Grothendieck Serre all the way back in 1958, which says that if I'm over an algebraically closed field, then if G is semi-simple, and I guess that means connected semi-simple. Actually, sorry, I think connected actually follows. So say it's semi-simple, and any étale locally trivial B bundle is Zariski locally trivial. And G is a product of copies of SLN of special linear groups and symplectic groups. Okay, so somehow this sort of rarely happens. Well,
wait, sorry, can you say a little bit about why it's not Zariski locally trivial
not this one,
spaces? Yeah.
for like the quadratic space, for example. I mean, yeah, maybe it's more of a heuristic argument, but it's just if you think about how do you trivialize a quadratic space, you pass to for example, like an algebraic closure. You don't need to go all the way to the algebraic closure generally. Think if you have like a non-trivial quadratic space over the real numbers, to trivialize it, I need to extend scalars to the complex numbers, right? Over which all quadratic forms are isomorphic. And that is an étale based change. It's not a Zariski based change.
Okay.
Right. So and you can, again, it's something you have to check is that basically, well, you know, if you think about it, if there were Zariski covering of R that trivialized it, it would have to already be true. There's not very many Zariski. Yeah. Other questions? So this is the reason why we use the étale topology. Because we are usually concerned with smooth group schemes, you know, and for us it'll probably be a reductive group over a field or whatever. It's kind of most common just to use the étale topology to define stacks, but you can use either the étale or fppf topology depending on taste and on the circumstances.
Does it have anything to do with the Galois homology of the group?
Yeah, absolutely. Yeah, I mean the obstruction to this.
So in particular, that's why the symplectic case groups.
Sorry.
That's why the symplectic case groups.
Maybe yeah.
I mean, that's why you still assume that symplectic groups.
yeah, you're alluding to some fact that I probably don't know. Some group homology vanishing, yeah, okay. So I admit I don't know the theorem at all, but again, you can go back and look at these notes. It's there from 1958, it's from the Claude Chevalier seminar. In particular, there was an exercise that I extracted that I wasn't able to do in the time that I could prepare this talk, which is Sarah gives an example of basically, he says, first of all, this is going to happen, that the any étale locally trivial torsor is Zariski locally trivial, if and only if, when I embed D into DLN, that the kind of G torsor I get by mapping DLN to DLN on G is Zariski locally trivial. Okay. So what he says is consider the case of the spectral orthogonal group, okay, and prove that this is not Zariski locally trivial. It's a really great exercise, and it comes down to something like the way Sarah phrased it is like the generic quadratic form cannot be trivialized over the field of rational functions generated by sort of the matrix coefficients and also the square root of the discriminant like this. So anyway, probably a difficult but really fun exercise to do.
Did you have to do things like other than completing some sort of H1 top?
I mean, I think it comes down to this ultimately.
This would have been before they had étale cohomology.
Yeah, exactly. Right. So, but you can definitely phrase it in some elementary way. That was to get out there. Yeah. Okay. Other questions? Okay, so I'm trying to decide what to do with the remaining time because there's not a whole lot left, and I did want to talk about representability. So I'll start talking. So I think I may be like halfway through my notes or something. I'll have to be returning here. So okay. So the last thing I wanted to talk about is so-called Artin stacks or algebraic stacks. I think the terms are more or less used interchangeably, but maybe the word algebraic is a little overloaded or something, so I'll call them Artin stacks. And these are supposed to be analogous to schemes, but in this stacky groupoid enriched world. In particular, they're supposed to be somehow locally isomorphic to affine schemes, right? In some topology. And this is the kind of thing that these classifying stacks are, or more interestingly, the BunG is. Okay. So we'd like to kind of formulate this condition. So, you know, certainly we'd like to require that these things are actually stacks, as it says in the name, right? But there's also some other condition or conditions you need to impose, right, to say that it's, like I said, kind of locally isomorphic to an affine scheme in some sense. So let me ask you a question. So let's take G to be smooth. Okay, so question is, in what sense is EG locally isomorphic? So I'll kind of ask the question in this simplest example of a classifying stack. In what sense is it locally isomorphic to an affine scheme? Okay, so the idea is that there's this distinguished map, respect K to BG. Oh, by the way, BG from now on means I'm assuming BG is smooth, so it's just use BG étale. The same thing as BG fppf. If it's not smooth, you should use BG. Okay, so there's this is supposed to be a smooth atlas. In the sense that a scheme has a Zariski atlas. Right, so an atlas is like, you know, the thing where you cover a scheme by affine scheme. The terminology comes from, I guess, differential geometry originally. But the idea is that this is supposed to somehow be the kind of covering that makes BG algebraic. So like, in what sense is this smooth? In what sense is it a covering? So one thing you can say right away is that if G is again smooth and affine, okay, then I can form this Cartesian square. So if I have some S point of BG, right, that classifies a étale locally trivial G torsor on S, right? And this map from spec K to BG, this is the one that classifies the trivial G bundle, right? This canonical guy classifies the trivial G bundle. And so if you think about it, this fiber product is exactly the total space of the G bundle that P classifies. Okay, this is how classifying stacks work. But again, extract it from the definition. And so in particular, you know, this map here is smooth and affine. Okay, it's the G torsor going to be smooth and affine. Okay. Smooth, affine, and of course surjective because it's a bundle. Okay. So, like, at least in this case, this is the sense in which this is a smooth atlas. It's supposed to be kind of smooth and surjective. So for any S scheme S mapping to BG, when I base change, I get a smooth surjection. Okay, so which is sort of a reasonable test, you know, for something to be smooth and surjective in the stacky world. So question is here, I want to beeline for the definition of an Artin stack, or do I want to linger on some weird subtleties that are not going to be relevant? I think I'm kind of tempted to linger on the weird subtleties because probably next week would be also a decent time to talk about the definition of an Artin stack. I don't know if the person that.
What do you mean by not relevant?
Well, because they'll be the kind of not relevant for BunG, I should say, like for this seminar directly. But
oh, go ahead. Subtleties, include them.
Great. Okay, so I want to give one example that, like, okay, again, for me, things that I wish somebody told me before. The definition of an Artin stack has this weird condition having to do with algebraic spaces, and I never understood it. Okay, so I want to kind of give an example to explain why this condition is necessary instead of something stronger. All right, so what I want to say is that if G is not affine, something kind of strange can happen here. Okay, so you might want to say, okay, this map is a smooth covering, it's a smooth surjective map in the sense that for any set scheme S mapping in here, the base change is going to be a scheme mapping smoothly and surjectively to S. That actually doesn't always happen. It's very strange. Okay, so this example did a Raynaud, and it's sort of complicated, so I definitely won't give it in detail, but I'll just say what it does. The Raynaud says there exists a necessarily like kind of non-regular thing K, an elliptic curve E over K, and an étale locally trivial E torsor E, okay, again over K, everything defined over spec K, such that E is not a scheme. Okay. And like you're probably wondering, like, well, what the heck is a torsor then? It's not a scheme. Well, if you look at the definition of a torsor, the way that Nick said it, everything he said. Well, okay, maybe not the way that he said it. So maybe take the definition, right, where you say it's just something, it's just some functor, okay, some sheaf or some free sheaf acted on by E, such that there's an étale covering of spec K over which it becomes the trivial torsion. Okay, that makes perfect sense for even an arbitrary functor, an arbitrary free sheaf, not necessarily a scheme. And I'm claiming there are such things, okay, which are not actually sheaves, they're not actually schemes, sorry. Over spec K.
I see.
Yeah. Over this same. Yeah, and so this can only happen for kind of a non-regular base scheme. So again, to emphasize what happens here is I have this kind of thing that I want to be a smooth atlas. The guy that classifies the trivial torsor. And then on the other hand, I have this non-trivial E torsor. I'm calling P here. This fiber product again is the total space of P. This P is actually not a scheme.
It is a functor into sets, though.
It's a functor, yeah, it's a functor sheaf even, but it's not a scheme. Someone was asking for examples of sheaves that aren't schemes earlier. This is another one.
What's the issue?
Sorry?
What was the issue for this not to be
Okay, think about what happens here. So it's étale locally trivial. So there's some étale covering the spec K over which this thing trivializes. So after an étale base change, it's locally isomorphic to the scheme.
so it's just an algebraic space.
It's an algebraic space, exactly, which is the thing that I was dancing around. So the thing about schemes is that if I take a scheme and I have some kind of étale equivalence relation on it. So this is like the kind of datum that's like analogous to in the Zariski setting, right? If I have a bunch of schemes and I have a bunch of isomorphisms on some open subsets of those schemes that are compatible, right? Then I can glue to get a scheme, right? If I say the same words in the étale topology, the statement is false. Okay, I can't generally glue schemes along étale equivalence relations, and this is exactly an example of something that fails. So this thing is étale locally a scheme, but it's not actually a scheme. So E is what's called an algebraic space. Okay.
But you can get easier examples by like the affine line equals now by finite groups in positive characters.
Easier examples of algebraic spaces, yes, certainly. But I was kind of trying to give one an example in the context of these classifying stacks. Yeah, I'm saying a classifying stack like doesn't all in this elliptic curve kind of situation. You don't even always have a schematic atlas. It's very weird. Again, not really relevant for the seminar so much because in the affine case everything is fine and this is a scheme and there's no problem here. So I just wanted to highlight this as the reason why if you look in Lamont and Murray Bailey's book Champ Algebraic, there's like this word representable by algebraic spaces keeps coming up. It's exactly because of this kind of thing. Okay. So, and even if you only care about geometry over a field, like this already comes up. So if I asked, again, algebraic geometry grad student, like what is the definition of the moduli space of algebraic curves of genus 1? Okay. They would probably give an incorrect definition. They would probably want to say, a family of algebraic curves is like a scheme mapping to the base scheme, flat and proper, such that the fibers are genus 1 or whatever. But such families need not be schemes in general, exactly because of this sort of example. This P is actually a family, right, of genus 1 algebraic curves, and yet the total space is not a scheme. Okay. So hopefully this is like even more evidence that you should think about schemes in this functor of point setting, because this is yet another place where locally ring spaces are just totally inadequate for dealing with stuff like this. So like the moduli of algebraic curves, you already kind of need to talk about these algebraic spaces.
So what's the correct definition?
Sorry?
So what's the correct definition using this
Oh,
language?
say the same thing, but instead of requiring that the total space of the family is a scheme, don't put any condition on it. It's just going to be some sheaf sets. And relatively, it'll be like, you know, proper flat, but the total space doesn't have to be a scheme.
You don't want it to, I don't know what an algebraic space is, but.
Yeah, it doesn't really matter.
But you don't need it to be an algebraic space to have.
No, you don't have to
want
require,
it.
it'll automatically be an algebraic space from the, if you set up the definition, but you don't have to put the word algebraic space in the definition.
I see, so you're
Yeah.
saying that if you just set it up with no conditions, it'll be an algebraic.
Yeah,
space.
just the total
Just
space
means
will
it's
just be
locally,
some sheaf, you know, mapping to the base, and then you require that like the fibers are kind of. Well, you have to formulate this the correct sense in which it's proper flat, and that will require some work, which, you know, you probably would have to read a text on algebraic spaces to understand exactly the right words to say. But yeah, my point is just, you know, there is some subtlety here, and you can't get away with just requiring families of curves to be schemes in all cases.
Got it.
Yeah. Other questions? All right, so I am out of time. So the question is,
Okay.
is it permissible to go 10 minutes to give the
Yeah.
definition?
Yeah, absolutely.
Awesome. Okay, so it'll be terse, and then next week, whoever's giving the talk next week can flush it out when they actually use these notions. Okay, so I guess what I'll do is I'll quickly define algebraic spaces and then Artin stacks. Without a ton of, well, I already gave some context, so let me just do that. So first of all, to define algebraic spaces, I need to define what it means for a morphism to be schematic. So if X and Y are pre-sheaves, then X mapping to Y is called schematic. Sometimes this word, instead people say representable by schemes or something, but the word representable again gets overloaded. Sometimes people just say representable, it's a total mess. So I'm going to use the word schematic, it's ambiguous. If for any S affine scheme S, and any map from S to Y, fiber product is a scheme. Okay, so it just means this morphism is fibered in schemes. Whenever I base change to a test affine scheme, I get a scheme. Okay. So this appears in the definition of algebraic space. Okay, and now algebraic spaces are defined as follows. So they'll be a priori required to be an étale sheaf. So notice we're in sheaves, not stacks yet. This is still in the world of set value functors. Algebraic spaces are not stacky. And I require the étale topology. I convince you that that's the natural thing to do. So we call X algebraic space. So the funny thing that happens here is, unlike in the world of schemes, you actually have to impose two conditions. Okay, so that there's this first condition was sort of redundant in the world of schemes, but for algebraic spaces, I need to say it. So the first condition is diagonal map is schematic. I don't really know. It's a hard thing to wrap your head around. Let me just keep going. And the point of this condition is for any scheme S mapping to X, that map will automatically be schematic. That condition is actually equivalent to this condition. Okay. And so what's going to happen now is the second condition. I require that there exists an étale covering. I guess I'll call these UI, where all the UI are affine schemes. Okay, and the question is, what does étale mean here anyway, right? Like, not entirely clear that that's meaningful, given that this X is just some sheaf. And so the point is that each UI mapping to X is actually schematic by part one, and for a schematic map, talking about condition like étale or flat or whatever is meaningful. Because you just do the same trick as ever, right? You say for any test scheme S mapping into X, the base paint, which will actually be a scheme mapping to S, that map is étale. Okay. So condition 2 is really only meaningful in view of condition 1, which is like one way to think about why you need condition 1. So again, these are you can think about the ways these arise is in general taking a scheme and modding out by some kind of étale equivalence relation. For example, a free action of a finite group would be a very typical example of that, right? And so these are probably some of the first, maybe the first place where people recognize algebraic spaces was sometimes when you have a free action of a finite group, the quotient, like in the level of sheaves, is not a scheme, but it will be an algebraic space. Okay, it'll have this kind of étale covering by a scheme, which is the quotient. All right. So, and then as sort of a complement to this definition, you can say what there's sort of a relative notion. So X and Y are again arbitrary free sheaves. Call a map representable in algebraic spaces. Lots of people just use the word representable, which is gives me a headache. And this means that you could probably guess, right? For any test scheme, affine scheme S, any map from S to Y. The fiber product is an algebraic space. Okay, so again, it's something that's fibered in algebraic spaces. Neither Y nor X need to be algebraic spaces, but all the scheme theoretic fibers of Y are. All right, and with that, I can define algebraic stacks. Let me just say words like flat, étale, etc. make sense for morphisms representable by algebraic spaces. The idea is, if the target is an affine scheme, and you really just have an algebraic space mapping to S, then you can pass to some étale covering of the total space, and then it makes sense to say that that's an étale map. That's your condition when the target is an affine scheme, and then generally you do the space. All right, finally. Put it here. Okay, so an Artin stack, a priori, it's going to be just a free stack satisfying étale descent. And there are, again, two conditions, kind of analogous to the ones defining an algebraic space. So condition 1 is that the diagonal map is representable by algebraic spaces. And condition 2 is that there exists, and let me just say this a little more carefully than I said that. So there exists some collection of maps from UI to X, but the UI are affine schemes. Note, these maps are automatically representable by algebraic spaces by condition 1. such that they assemble into an étale covering. Sorry, smooth covering. Point is a smooth covering. Okay, so crucially, that makes sense by this remark. I realize now I should have erased that panel and not the other one. I wanted to point out, this is exactly the kind of thing you have to do to capture examples like, for example, B of that weird elliptic curve. So in that case, the kind of smooth atlas that's given by the map for spec K classifying the trivial bundle, as I pointed out, it's not schematic, but it is representable by algebraic spaces. Okay, which is why I only put this condition here. I don't require that this is schematic. It's required that it's representable by algebraic spaces. And here I require that the map is smooth and not étale because, well, that's the whole thing about stacks, right? Is like you can mod out by families of automorphisms of positive dimension, right? So like this map is going to have, in general, positive relative dimension, just like in the case of a classifying stack, right? All right. So that is the definition of an Artin stack, and I should probably stop there.
Any questions?
Are all of them algebraic species quoted by like étale equivalence relation?
Yes. Quotients of schemes by étale equivalence relations, yeah. Yeah. And you can see this because it has an étale covering by a scheme by definition. And you can actually construct an étale equivalence relation on the total space of that atlas, right? Yeah. Such that X is the quotient. Likewise, a Artin stack in general will be a quotient of an algebraic space by a smooth groupoid. Okay, not necessarily an equivalence relation because, well, related to the fact that the diagonal in the stacky world need not be a monomorphism, right? Again, it could have kind of points have automorphisms, and those automorphisms may have kind of positive dimension themselves. So in general, you have to quotient out by a groupoid, just like we get BG by quotienting out a point by a group, right? Which could be something like GLM. Questions? Yeah.
If in the representable by algebraic space, if Y is a étale sheet, is X automatically an étale sheet?
Yeah. Yeah. Huh? That's right. Questions?
So I just have a question. The representability by the diagonal, what that sort of gives you, if I recall correctly, is that basically the collection of automorphisms themselves form schemes, right?
Absolutely, yeah.
So like if you take a
More generally, the like isomorphisms between 2 points will kind of assemble into a scheme.
yeah.
The sort of
With any
transporters.
S points.
The transporters are yeah, exactly.
Yeah, and an S point fiber changed over the diagonal is the isomorphism.
And that's a good way to think about it, right? It's like we're not just requiring that we have a smooth atlas, we're also requiring that like the automorphisms of points kind of fit into algebraic families as well. Which is something that you didn't have to think about in the case of algebraic spaces or something because there were no automorphisms.
So loosely, the H0, the isomorphism classes of the objects in the groupoid form a scheme thing. And the H1s do too. All the automorphisms do as well, right?
Yep, exactly. Cool. Else?
Thank you.